So we're going to look now at conductors. And because we're dealing with conductors, we're going to be looking at the flow of electric current. A current happens when there's a flow of charge carriers. That means any charged particle. We're used to thinking about electrons inside wires when we think of electricity, but it's not the only time that we have a flow of charge carriers. Another example is when we have an electrolyte inside a process called electrolysis in chemistry. There it's a movement of positive ions and negative ions from one terminal to the other. Both of these demonstrate current. Conductors carry electricity, and we'll refer to it as that for now, because of their bonding. They have free conducting electrons, and these react to an external power supply by moving in a particular direction. But they're moving before a power supply is applied. Before you switch on your battery or your power supply, they're moving randomly at high speeds. There's no net movement of charge in any one direction. However, when you connect a cell, and by a cell we mean a small battery or a power supply, across the ends of the metal, an electric field is created, like the ones we talked about in the previous lesson. These electric fields cause the electrons to start to drift towards the positive terminal. Why do they drift towards the positive terminal? Because electrons are negative, and they're attracted to it. By drift, we mean that these random movements continue to be slightly random, but there tends to be a tendency now for the drift to be towards the positive. It's this motion towards the positive that's called an electric current. So to sum up, what is an electric current? It's the consequence of applying an electric field to free conducting electrons who feel a net force and so move towards the positive terminal. So now we know what's going on, we can define electric current. The electric current can now be defined as the amount of charge, the amount of electrons that move through the cross-sectional area of a wire per unit time. Another way of expressing this is that electric current is defined as the rate of flow of charge. I equals delta Q over delta T. Rate always means divided by time, and Q is flow of charge. Current I is a scalar and has units of amperes, A. The ampere, if you remember from last year, is a fundamental SI unit and can be expressed as 1 coulomb per second. So 1 ampere would be equivalent to 1 coulomb flowing in 1 second. So we mentioned how current was electrons moving towards a positive terminal. I wish it was that easy. Unfortunately, that's not the way that we refer to the direction of electric current, because in 1752, before the electron was actually even understood, so they didn't really know these electrons existed, Ben Franklin chose a convention regarding the direction of current flow. He just made it up. He assumed that electrons were positive, and so he thought that they were moving from the positive to the negative terminals. We know this is incorrect, but we still use this direction as the convention. So the conventional current flow, the direction that we say the current is moving, is actually opposite to this common sense model that we described before. Okay, so conventional current is towards the negative terminal of your battery, because that's what it used to be before electrons were discovered, and that is what you use as your convention. It's not so important with current, but when you do things with the electric motor and magnetic field and electromagnets, the conventional current is still used, and there it's super important. So you just have to remember that it's the opposite of common sense. So this is the sensible flow, the electron flow of current, which was then kind of announced when the electron was found to be negative. But by then, we already had this convention. So how quickly do these electrons flow? The electrons move randomly at speeds of a magnitude of 10 to the 5 meters per second. But that's within their random motion. Once they actually start drifting across the metal to reach the positive terminals, they're going remarkably slowly. The electrons are allowed to drift. And these electrons, of course, are constantly colliding with other ions. The actual movement is really, really slow, which is strange because when you switch on the electricity or your light, if you switch on your light switch, the light comes on instantly. How can that be true? Now for that, you need to watch the next video. But for now, we're going to carry on with this idea of the drift velocity, which is the velocity that the electrons actually move across the wire. We can actually work out the drift velocity, or we can work out the current from the drift velocity using this relationship, where current, I, equals the number of charge carriers, so how many coulombs of charge are there per meter squared, the cross-sectional area of the conductor, the drift velocity, which is v, and the charge on each carrier. Okay, so the amount of charge carriers times the cross-sectional area of the wire times the drift speed of the charge carriers times the charge on them. This would give you the total current. And you can rearrange this formula to actually work out the drift speed, which would be the current divided by the number of charge carriers, the area, and the charge. Don't forget the current is in amperes. Here's a nice question to practice. This is unit analysis. Try checking to see if the units on the left-hand side match the units on the right-hand side. I'll give you a moment, switch off the video, see if you can work out the total unit left over on this side, and see if it matches with this side. Okay, so let's have a look. We have number of particles per meter squared, which is m to the minus 3. You have the area, which is meters squared. We have speed, meters per second, and charge, which is coulombs. Now expanding coulombs are current times time, amperes times seconds. If we look at the meters, we have m to the minus 3, m to the 2, and m, which cancel out. And we're left with s to the minus 1 and s, which also cancel out. And we're left with amperes and amperes.